Welcome, my name is Dr. DrWedding, and this is DrWedding, DC11. DC power and resistor wattage ratings. In this video, you will learn how to calculate the power delivered to a resistor by the power supply. Once this value is calculated, a wattage rating for the resistor is chosen that will be large enough to handle the power. Assume you need to cross a river, and the river was flowing at 3 miles per hour. If the water was 2 inches deep, you could just walk across it. If the water was 3 feet deep, you would struggle to get across it. And if the water was 10 feet deep, you would be swept downstream. Now assume you needed to cross the same river, but this time it is 2 feet deep. If the water is flowing at 1 mile per hour, you could easily get to the other side. If the water is flowing at 5 miles per hour, you might be able to get across it. And if the water is flowing at 20 miles per hour, you are not going to make it. So just like a river becomes more powerful as it gets deeper, a supply delivers more power as the voltage increases. And just like a river becomes more powerful as the current increases, a supply delivers more power as the current increases. If you think about power like this, you can see that power has a voltage component as well as a current component. When a power supply is connected to a resistor, power is delivered to the resistor. The equation used to calculate this power is P equals V times I. The unit of power is the watt. Furthermore, Ohm's law and the power equation can be combined to generate even more equations. 2 examples are shown below. In the first equation, you can start with P equals V times I, but you replace the V with I times R from Ohm's law. This will give you a new equation. P equals I squared times R. In the second equation, you can also start with P equals V times I, but this time replace the I with V over R from Ohm's law, and you will generate the equation P equals V squared divided by R. If you take Ohm's law, the power equation, and all of the combined equations, the following circle can be generated. To use this circle, the value in the inner circle is equal to 3 equations in the same quadrant. This circle has Ohm's law with each variable isolated. The power equation with each of the variables isolated is also on this circle. Assume you need to find a resistor value. So you go to the blue wedge, and there are 3 equations to choose from. If you were given voltage and power, then you would use the equation R equals V squared over P. Let's use the circle to find the missing value. Example 1. A resistor has 2 volts across it and 15 milliamps through it. How much power is delivered to the resistor? Because you are looking for power, you will go to the top left part of the circle that is colored orange. You were given voltage and current, so you look at the 3 equations to see which one uses voltage and current. So the equation you will use is P equals V times I. By plugging in the numbers, you can quickly find the power delivered to the resistor is 30 milliwatts. Example 2. A 1 kilo ohm resistor has 4 volts across it. How much power is delivered to the resistor? Because you are looking for power, you will go to the top left part of the circle that is colored orange. You were given voltage and resistance, so you look at the 3 equations to see which one uses V and R. So the equation you will use is P equals V squared over R. By plugging in the numbers, you can quickly find the power delivered to the resistor is 16 milliwatts. Using the circle, you can solve a circuit as well as find the power that is delivered to each resistor. But how does that help you? The power that is delivered to the resistor is converted into heat, where it is dissipated into the air. The equation that calculates the amount of heat, in joules, is not covered in this video. But it is important to understand that the more power that is delivered to the resistor, the hotter the resistor will become. Therefore, the resistor must be able to withstand the heat, or it will burn up. In order to understand the wattage ratings on a resistor, you first need to understand thermal mass. Thermal mass is a term that means an object has the ability to store and release heat. If more heat enters the object than it can handle, it will be damaged. Assume you have a block of iron that has been heated up in a forge until it is glowing red. Now you need to cool it down so you can pick it up with your hand. If you tried to cool it down with a glass of water, you would not be very successful. This small amount of water would not cool it down, and when you touched the block with your hands, you would be seriously injured. If you tried to cool it down with a 55-gallon drum of water, you would be more successful than with a cup of water. Even though the block would be cooler than before, you would still injure your hands if you touched the block. If you tossed the iron block into an Olympic-sized swimming pool, the block would easily cool down. And after a short time, you would be able to pick up the block without damaging your hands. In the iron block experiment, the amount of heat was the same. The difference was the amount of water used to cool it down. As the number of water molecules increased, the amount of heat each of the molecules needed to absorb decreased. Just like you needed more water to cool down a large block of hot iron, you need a larger resistor to withstand more power. All of these resistors are 1 kilo-ohm resistors. The only difference is their physical size. Resistors under 1 watt are in standard increments. The resistors are cut in half with each step. A 1-watt resistor can withstand 1,000 milliwatts without damage. The next size down is a half-watt resistor that can withstand 500 milliwatts without damage. The next size down is a quarter-watt resistor, then an 1/8 watt, and then a 1/16 watt. There are smaller resistors, but they are not going to be discussed in this video series. Now that you have access to different resistors that can withstand different wattages, you need to pick one for your application. Unfortunately, there are no hard rules that determine what size resistor you need. Think of it like this. Assume you have a car that you need to jack up in the air so you can fix it. The car weighs 1,475 pounds. You go to the parts store, and they have a jack that will max out at 1,500 pounds. Your car is under the maximum rating by 25 pounds. The jack is the smallest, and it is the lowest price jack. Is that the best choice? The store also has a jack that is rated for 2,500 pounds. This jack is safer because it has a larger maximum rating, but it is bigger and costs more. So is it the best choice? The store also has a jack that is rated for 6,000 pounds. This jack is much safer because it has a larger maximum rating, but it is a lot bigger and costs a lot more. But you may need a larger jack sometime in the future if you end up getting a bigger car. But is it the best choice? Just like picking a jack for your car is not a clear decision, picking the wattage rating of a resistor is also not a clear decision. Every teacher, book, and employer will have their own rules for picking a resistor. The size of an object is often chosen using a safety factor. A safety factor is a value you multiply the load by in order to determine how strong an object needs to be in order to be safe. Assume you have a safety factor of 1.5. You would multiply your car's weight by 1.5, and you would say, I need a jack that can handle 2,213 pounds. Using this safety factor, the 2,500-pound jack would be your choice. In this series, I will use a safety factor of 2 when choosing my resistor values. Now that we have covered the power calculations and understand what the wattage rating is, let's solve this series circuit. This time the table will include a column for power and one for the wattage rating of the resistor. We have solved these types of problems before, so the first part of this problem should be a review. In a series circuit, the total resistance is the sum of all the resistors. Once you have the total resistance, you can use Ohm's law and the total voltage to find the total current. Once you have the total current, you know all of the currents, because all of the currents are the same in a series circuit. With I and R, you can calculate the voltage drop across each resistor using Ohm's law. The calculated values are then copied to the original circuit. To double-check your work, you can apply Kirchhoff's voltage law. Because the voltages around the closed path is equal to 0, there is a very good chance the values are correct. Using the voltage and the current, the power delivered to each resistor can be calculated. Note, when multiplying a volt times an amp, you get a watt. So the power delivered to R1 is 39 milliwatts. And the power delivered to R2 is 70.3 milliwatts. And the power delivered to R3 is 14.1 milliwatts. The total power that the supply must deliver to the circuit is calculated the same way. Total power is the total voltage times the total current. In this example, the supply must be able to handle a minimum of 125 milliwatts. Using the calculated power, you will need to select the correct size resistor to prevent it from being destroyed by heat. Note, different books, different instructors, and different employers may perform the next step differently. In this video series, I will assume a safety factor of 2. This means I will use the smallest wattage rating that can handle twice the power delivered to the resistor. So for resistor R1, I will multiply the power by my safety factor of 2. This means I need the smallest resistor that can handle 78 milliwatts. Starting from the smallest resistor, the 1/16 watt resistor will not be able to handle the 78 milliwatts. So I will move up to the 1/8 watt resistor. This resistor can handle 125 milliwatts, so this resistor needs to have a 1/8 watt rating. For resistor R2, I will multiply the power by my safety factor of 2. This means I need the smallest resistor that can handle 140.6 milliwatts. Starting from the smallest resistor and working my way up, the smallest resistor that can handle 140.6 milliwatts is a 1/4 watt resistor. For resistor R3, I will multiply the power by my safety factor of 2. This means I need the smallest resistor that can handle 28.2 milliwatts. And working up from the smallest resistor, the first resistor that can handle the power is the 1/16 watt resistor. The total power is not a resistor. It is the minimum rating the power supply needs to be in order to power the circuit. Some people may use a larger safety factor for the total, but in this series I will calculate it with a safety factor of 2, just like the resistors. The total power is 250 milliwatts, so the power supply must be at least a 1/4 watt supply. I hope that this video has helped you understand how to calculate the power delivered to a resistor, how to use the V, I, R, P circle, why you need to calculate the wattage rating of a resistor in a circuit, and how to pick the wattage rating of the resistor based on the power so the resistor does not get damaged. If you find these videos helpful, please like the video, leave a comment, and subscribe to my channel. This is the only way I can continue to make these videos.